Here's another lecture of the video of the lecture Intro PDE. In this lecture we present the first half of section 3.2. So we don't present the full section, we only present the first half of section 3.2. This section is called mean value property. Okay, and in this first half we really will prove the mean value property and introduce the weak mean value property. So, what is the mean value property? Let us immediately introduce the mean value property. It's an equivalence. So, we have an open subset omega of Rn. We have an open subset omega. Omega is an open subset Mrn. And now we look for a ball whose closure is contained in omega. So we have here x, and we have x, and we have the ball B of x r with radius r. And we assume that the closure, so also the boundary of this ball, also contains to omega. We assume that B of x r closure is contained in omega. Now the closure is then of course a compact subset of omega. And then we take the mean of u on the ball. What is the mean? The mean is the integral. So we take integral of u of y over this ball dny, dny. So we integrate over the ball and we divide by the volume of the ball. And the volume of B of x r, okay, this is omega n, the volume of the unit ball, times, of course, r to the power of n. Since by rescaling the volume in an n-dimensional space scales by r to the power of n, because all dimensions are scaled. So everything scales, all dimensions scales by r. Since we have n dimensions, it scales by r to the power of n. So this is the mean of the ball on the ball or on its boundary. Okay, and now the claim is the area of the boundary of xr. This is sigma n times r to the power n minus 1. Since it's n one dimension less, it scales the area scales by one dimension, by one power less. Since we have one, we don't have the radius itself, which scales. It has one dimension less. And sigma n, we saw this in last section, it's omega n times n. So it's really n mal omega n mal r to the power of n minus 1. So the mean over the ball, over the boundary of the ball is this expression. And now d sigma. This sigma, this is this boundary integral, which we introduced in the section in the chapter 2. Mean over the ball, and here we have the mean over the boundary of the ball. Okay, and now the claim is, if the function u is twice continuously differentiable and harmonic, then we have that the mean of u on the ball and on its boundary is equal to the value at the center. So we have this equation and we have this equation. So we have these two equations, For harmonic functions, we have these two equations. Conversely, if the means of the a function, now we assume again u should be twice continuously differentiable function. And if the mean of all balls with compact closure, so whose closure belong to the omega set, the full compact closure in Rn is a subset of omega. If the means of this function is equal to the value at u of x, and for all balls, or we have two possibilities, or if this holds for all and the means for all boundaries of all balls, then u is harmonic. So we have a characterization by harmonic functions by two properties. Okay, so now let's look at the proof. The proof, and you will see the proof is mainly a consequence of the divergence theory. This is really a nice statement, and it follows from the divergence theory. Okay, we define this function phi of r. We choose some ball with compact closure. We choose here such a ball. And now we choose a center. And then we have all concentric balls with radius r. And define now a function phi of r, which is defined for all radius such that the corresponding ball of radius r with its closure belongs to omega. Okay, and then we define as the mean over the boundary. Here we define it as the mean over the boundary. So n mal omega n omega n integral of u of y d sigma of y and over xr over the boundary. Now this is our function. Okay, and now we do a calculation. The aim is to calculate the derivative. Now we want to calculate the derivative. Okay, here we have a problem, and the problem is that this variable r also is in the domain, and then we don't know how to differentiate. So we should first make a transformation such that this is not anymore in the domain. But this is rather simple, because we make just a transformation. We transform it and integrate now over the unique ball. This has volume area n times omega n, so the mean over the unique ball. And if set runs over the unique ball, then x plus r set runs over the ball of radius r around x, and the same for the boundaries. So here we take the mean over the boundary of the unique ball and for the coordinate z, which means if z runs through the boundary of the unique ball, then x plus rz runs through, if z runs through the boundary of the unique ball when x plus r set runs through the boundary of the ball xr. We translate it by x such that unique 0 is shifted to x and the radius is rescaled by r such that okay, so we clearly have this formula. Observe that the rescaling of this ball is just a factor n to the power of r n minus 1. Okay, so we have this. Now we can differentiate. Here, the only place where r shows up is here. And clearly, since this is a continuously differentiable function, we can differentiate with respect to r. Now let's differentiate with respect to r. Here we do it. Then we should phi prime of r is now 1 over n omega n integral. And now we should take the derivative with respect to r of phi, not phi, u. Of u of x plus z r d sigma of z. D sigma of okay, and this we can calculate the derivative with respect to r. Okay, this is 1n omega n integral, so it's the gradient, that's the outer, and the inner derivative is just z. U of x plus r times z, z d sigma of z. And this was over the boundary of the unique ball. And now we transform back. Since by scaling we again get n r to the power n minus n omega n. We get the ball, the boundary of the ball with radius r. This of course does not change. But this vector set, since if we have here this ball, then this vector set, this is just this vector. If we put it here, it's just the outer normal and it's normalized. So we may write it as the outer normal d sigma of y. This is the outer normal n. Okay, so set these vectors are equal. Now we can apply the divergence theory. This is the right hand side of the divergence theorem. So we get 1 over n r n minus 1 omega n. And now we should take the divergence of the gradient. Now we should integrate, of course, over the ball. But the divergence of the gradient is Laplacian. Laplacian u of y dn of y. So we get this. And since the Laplacian vanishes, our function is harmonic, we have this is 0. So this means our function phi is constant. Phi is constant. For all r with such that the closure is contained in omega. This is constant. Now we will take the limit when n goes to 0, when r goes to 0. Yeah? Now we will consider the limit when r goes to 0. Okay, and now we claim that for r to 0, phi of r goes to u of x by continuity of u. Okay, let's see. Let's calculate the difference, minus u of x, absolute value. This is, of course, just the integral. I rewrite it once more. Omega n integral over the boundary of the ball, u of y, d sigma of y minus u of x. Yeah, and now comes the crucial observation. Since this is the mean, yeah, also since integral 1 over, or write it without 1, since just the integral d sigma of the, since this is n omega n times r to the n minus 1. Yeah, so if we divide it, this is 1. Yeah, and of course everything is linear. So by this we obtain, we may write this constant differently. We can write it in the following form. Integral u of y minus u of x, and the whole thing d sigma of y, u of x, and absolute value. Why? Yeah, because u of x doesn't depend on y, so we can put this out of the integral, and then we just get this number, so we get just u of x times 1. Yeah, so this is indeed the same. And now, clearly, this is smaller if we put the integral, the absolute value inside, yeah, by the triangle equation. So integral of u of y minus u of x d sigma of y. Okay, and now for sufficiently small r, yeah, then this ball, oh, I forgot here, we have the boundary of xr, boundary of xr. We are contained in an arbitrary small epsilon ball or delta ball. Yeah, then we have u of y minus u of x smaller than epsilon for all y in this boundary. Yeah, since it's by continuity. Yeah, this is the continuity. And this, and then, yeah, since this is a mean, then this is smaller or equal epsilon. Yeah, indeed, by continuity, it's really smaller than epsilon. Yeah, but this is not important. So, also since here, this is the argument. Yeah, so this becomes arbitrarily small. Yeah, for sufficiently small. Yeah, so we see, and this proves now the convergency. Yeah, so now we really see that this converges. So limit r goes to 0, phi of r is u of x. Yeah, and since we have proven that phi of r is constant, yeah, since phi of r is constant, we have that it's this equality phi of r is equal to u of x. Yeah? For all r with such that the ball is contained in omega. Okay, now we proved one thing. We proved the mean value property for the means over the boundary of the balls. Now we want to prove also the second part. Yeah, now we want to prove also the part over the means over the balls. Yeah, but the means over the balls, these are 1 over Rn omega n over the balls u of y. Yeah, this is the mean over. But this we may write. Yeah, this we may write as an integral over the means over the boundaries, yeah, by polar coordinates. So we write this in this way: 0 to r 1 over s. Yeah, the omega n we put in, yeah, but this other factor we leave out. And since we want to put in n omega n, s n minus 1, integral over the means over, so the means over the boundaries of the balls with radius s, u of y d sigma of y, and then integrate over s ds. Yeah? Yeah, this should be in ds here. Now, since we already know that this is always, for all s, this is u of x, so this is n over Rn, 0 to r, what is u of x? This whole thing, so this whole thing, u of x, and then we obtain then we obtain sorry, I forgot here to write, of course, since we divided, we have to here write Sn minus 1. Yeah, okay, so we get u of x times Sn minus 1 ds. Yeah, and so, yeah, since this here is the mean over the ball, which we already know is constant. Yeah, so we obtain this, and now we can integrate. Yeah, this we can integrate, and then it's clearly n over Rn, and this integral, the antiderivative of this function is u of x, and then times s to the power of n over n from 0 to r. Yeah, and then you see, then we get n cancels, r cancels, so it's really u of x. So this indeed shows that that we also have that the means over the balls are for an harmonic function equal to the value at the center. Yeah. So we first proved this for the boundary of the balls, and then we used polar coordinates in order to calculate the mean over the ball in terms as an integral over the means over the boundary of the balls, of all balls of radius s, where s runs from 0 to r. Yeah, and okay, here this is Also maybe I write this differently to make this more clear. We write here S n minus 1. Yeah, the n omega n, so this is clear. This expression here, this is the mean over the yeah, this is u, this is the mean over the boundary of the ball. And this is constantly equal to x. So we get, okay, I also reverse the order. So we really get S n minus 1 times u of x, and then integrate this, and then we get u of x. Okay, so we see, now we have proven one direction. Now comes the other direction. Yeah, now the other direction. Conversely, let u be 2 times continuously differentiable on omega. And let's assume that for all balls, yeah, and now we first start again with the statement of the boundary of the balls. Yeah, no, sorry, now this time we start with the balls, conversely. And u of x is equal to 1, if we first consider the following statement. Over the balls are n omega n integral u of y d over all balls if the closure of the ball is inside of omega. Yeah? Let's assume that this holds. Yeah? That this holds. Then we can again use this nice formula. Yeah? Here. Then we know that we have this formula. Yeah? So this is the same as n over Rn, 0 to R, over s to the power of n minus 1 phi of s ds. Okay, so we now know that this equation holds. Yeah, we know that this equation holds where phi is the mean over the boundary of the balls. Yeah, here, this we already derived. Okay, so this means, yeah, this means d by dr of n over Rn, 0 to R Sn minus 1 phi of s ds. This is 0. Yeah, this derivative is 0. Now let's calculate. We have two places where this depends on R. Yeah? As we know, this means we have to take at both places the derivative and then take the sum. Yeah? This follows from the chain rule. I hope this is clear. Otherwise, please ask me in some answer and question section, and then I will explain this. Okay, so okay, so now we calculate this derivative. Then we first have here minus n so we get minus n squared over Rn plus 1. Yeah, if we take here the derivative, 0 to R Sn minus 1 phi of s ds. This integral goes to R. Now if we differentiate here, yeah, then we have this factor plus n over Rn, And now, by the fundamental theorem of calculus, if we take here the derivative, we should set s equal to r. So we get r n minus 1 phi of r. So we have these two terms. Okay, this term here, this differs from this term here by this whole integral only by a minus n over r. Minus n over r, and the rest we know already is u of x. And here we have a plus n over r, everything else cancels, so we have this equation. Since this is 0, so we get phi of r is equal to u of x. So this means, oh, sorry, I don't know what happened, that I think I erased some. Okay, now I will continue downstairs, yeah. So this means that phi of r is equal to u of x for all such balls. Yeah, okay, this means whenever the closure of this ball belongs to omega, then phi of r is equal to u of x. So we started with the assumption that the means over the balls are equal to the values at the centers. And we obtained that the means over the boundaries over the balls are equal to the center. So if the means, this means if the means of u over the balls are equal to u of x, yeah, for all radius such that and so on, then also the means over the boundaries of the balls are equal. Yeah, this we have proven to u of x. Yeah, since we know this function is differentiable and we calculate, we just know that if this is constant for all r, then we get from the derivative that this equality, yeah, that the vanishing of the derivative. Okay, now we know that in both cases, so if either for all balls whose closure are contained in omega, the means over the balls are equal to the values at the centers, or if the same holds for the means over all boundaries of the boundaries of the balls for all these balls, then the second statement holds. Okay, and now we may use the calculation of this derivative. Yeah, now we know that this derivative vanishes. Yeah? Then we conclude that the integral, this is some constant, we conclude that the integral over vanishes for all balls whose closure are contained in omega. Now, if du of x is non-zero for some x in omega, then by continuity of u we assume to be twice continuously differentiable. So this is a continuous real functions. Yeah, there exists a small ball such that we now such that either if du of x is negative, that this is smaller, we assume du of x half, absolute value, yeah, on the ball b of x r. Yeah, if this is negative, yeah, then if d delta of x half is negative, yeah, then we may find a small ball that is smaller than minus d half, yeah, because we can make the distance to this smaller than the absolute value half. Or, yeah, this is the case if du of x is smaller than 0, or du is larger d of x half on this ball. Yeah, if du of x is larger than 0. Okay, in both cases, this clearly implies that then the integral over du d mu over this ball here, this very small ball, is non-zero. So we get a contradiction when we find any point which is non-zero. Yeah? If any point is non-zero, then we get a contradiction. Yeah? So du is 0. Okay, and so since du is 0, u is harmonic. U is harmonic. Yeah? And this shows the reverse inequality. Yeah? Now we have proven the reverse inequality. Okay, very nice. Yeah? Now we proved both directions. Now we go further. Now we will have several implications of this theory. Now we will have several implications of this theory. First implication, yeah. Let u be a smooth harmonic function, and we will see later, yeah, that we can weaken the condition. It will be enough later if u is just measurable and bounded. Okay, also if u is a smooth harmonic function on an open domain and bxr a ball with compact closure in omega, then for all multi-indices we have the estimate, so we can estimate the value of the derivative with multi-index alpha, partial derivative of u of x at the center of the ball by some constant and some inverse power of r and this supremum on the ball. A supremum on the whole ball. And here we have an explicit given the constants, yeah, explicitly. Okay. Proof. Yeah, the proof, we only use now the mean value property and the divergence theorem. Okay. So we choose E 1 to n, and now we choose the half the ball. Okay, now we calculate here this. Also, let's follow here this calculation. We take this derivative. Yeah, this is partial derivative in the direction of I, so we add one more partial derivative, yeah, because we want to use an inductive argument. Okay, then here you see this is r half to the, this is 1 divided by omega n, r half to the power of n. Yeah, then since this we may write 2 to the power of n divided by r. Yeah, this is of course 2 to the power of n omega n r to the power of n. Okay, and then we have this. This is by the mean value property. Yeah? This is the mean over the ball with radius r half. This is really the mean over the ball of radius r half. And of course, if we have a harmonic function, then all partial derivatives, yeah, di d alpha u, is also harmonic. Yeah, since if we apply Laplacian, then this is the same, since everything commutes, and this is 0. Yeah, so all these functions are also harmonic. So we may apply the mean value property to this function, and this is exactly this formula, yeah, with absolute values. And now we apply the divergence theorem. Yeah, since here we have a derivative, by the divergence theorem, yeah, since if we use the vector field, which only has in the ith component this expression here, yeah, then the scalar product with the normal gives this here, yeah, and this is the divergence of this vector field, which has this components. Okay, so we see this is the divergence of a vector field which only has in the ith component this function. Yeah, and this is now the boundary term of the divergence theorem. Okay, and this we may estimate here. This we may estimate since here we have also 2n to the power of n times omega n times Rn is of course the same, I claim, as 2n over r, and now times 1 over omega n times r half n minus 1. Yeah, since this 2r's gives Rn minus 1, here we have the omega n, the n cancels, here we have 2, and here we have 2 to the power of n minus 1, together they give 2 to the power of n. So this is the same. So if we insert this here, then we see that this is 2n over r times the mean of this function. Okay, so this is so we have, so we can evaluate this. Yeah, we can evaluate this by the supremum's norm and of this function times this factor. Yeah, and the ni is of course, ni absolute value is of course always smaller than 1, because the normal has length 1, so all components are at most 1. So we have this estimate here. Yeah, this is now our estimate, and now we apply this estimate inductively. So what is now the idea? Yeah, we only need this estimate. As a first the claim is for alpha equals 0. Yeah, for alpha equals 0, the index no derivative. Yeah, we get an estimate for all first partial derivatives. So this means we have Cn1. We may just choose as 2n. Yeah, 2n. Yeah, since in this estimate here we have, for when the length is 1, we have 1 divided by r, so the power of r is correct. So this number should be 2n, yeah, for first partial derivatives. And on the other hand, yeah, we may use this as an induction whenever we have a multi-index of length alpha plus 1. Yeah, so then it's of this form. Any multi-index of length alpha plus 1 looks like this. Okay, so we obtain this estimate here, yeah. So we obtain this estimate. So we and now we use induction by the length of alpha. So we assume that this holds here for alpha for some particular length of alpha, and then we want to prove it for if the length is one larger. Yeah, then we have here this and have this estimate, and we already know that this is smaller than this constant. Yeah, so we get that we have here this constant and an additional factor 2n over r. So this means the constant, if we increased the length of the multi-index by 1, yeah, then we get, what we get is, we need to evaluate at the half the radii. Yeah, so we get the power here from this. We get the powers 2 to the absolute value of alpha, and we get one additional factor 2 due to this factor. Okay, and then we get this, and we get this constant. Yeah, so we really see that we get this recursive relation on this constants. Yeah, and now it's quite easy to see that we get immediately this solution of this constants. Yeah. Okay, once more, why, how comes this powers of 2? There's one, this 1 comes from this 2, and since we have here the radio 1/2, yeah, we get an additional factor of 2 of 2, and since we have here minus alpha, so we get a 2 to the power of the length of alpha. Yeah, so this is how this factor comes, and this n comes from here. Okay, whenever we increase the length of the multi-index by 1, we get an additional n, and we get these powers. So these powers which we get are the sum over all numbers over all lengths from 0 to the length. So this is well known, yeah, the summation formula. This is the sum over all lengths from 1 to the length of alpha. So for this reason we have this fact power of 2 and n to the power of alpha. Yeah? Okay, so this is our formula, and this proves this theory. Yeah, this is very nice estimate. Yeah, so we have a very nice estimate for the value of any derivative in terms of the supremum norm on a ball of radius r. And this has a very interesting consequence. Yeah, there exist many theorems of Liouville, but this is one of his most famous theorems of Liouville. On a bounded set, on Rn, so an entire harmonic function, a function which is defined on the whole Rn, or whole Euclidean space, and which is bounded, this has to be constant. Okay, the reason is quite simple. We take the first derivative, apply this estimate. Yeah, since it's bounded, this constant is bounded. The length is 1. So we see that the value is always bounded by some uniform bounded number divided by r. since it's defined on the whole plane, this is now important, we can make the radius arbitrarily large. And then this goes to 0, so it's smaller than every positive constant. So in the limit it goes to 0, so the derivative has to be 0. And if the derivative is 0, then it's constant. Of course, there exists global bounded harmonic functions, namely the constants. So these are the only global harmonic functions. Okay. Now, in the next step, yeah, we want to generalize the mean value property to a property of harmonic distributions. So first, maybe look at harmonic distributions. Harmonic distributions. So this is some f in d prime of omega with Laplace f is 0. But what is Laplace f? What is Laplace f? Laplace f, this is, remember, it's a linear map. Yeah, and it maps phi to, and since it's a second derivative for all the derivatives are defined, yeah, dif of phi is just minus f of di phi. If we apply this twice, then we get prime plus square plus square. And now we take the sum. So it's just f of Laplace phi. So the distribution is 0 if and only if f vanishes on the image of on all test functions of this form. Yeah? If f vanishes on all test functions of this form. And what we want to prove later, this we don't do today in this lecture, we do it in the next lecture. In the next lecture we will see that any distribution which is harmonic in this sense, which has this property, comes from a harmonic function, from a smooth harmonic function. This is Wild's lemma. Yeah? This is very, very strong statement. Yeah? Because remember, we had a regularity. The distributions were the lowest regularities. Yeah? And the smooth functions are almost the highest regularity. So every harmonic distribution, so something harmonic of the lowest regularity, is automatically harmonic of the highest regularity. Yeah, this is a typical property for elliptic theory and a very important property. So the equation itself forces the solutions to have high regularity. Yeah? Even if you start with a solution of lowest regularity, the solution automatically has highest regularity. This is very strong theory, and to prove this we need some preparation. Yeah, we first prove one direction. We first prove that that a harmonic distribution has some kind of weak mean value property. Okay, we first prove. So we first prove that a harmonic distribution has some weak mean value property. So in order to do this, we should formulate the mean value property for distributions. Yeah, and I claim, yeah, by the mean value property, here we do a simple short calculation. And this will help us to formulate the mean. Sorry, what happens here? I insert a page in between. This is of course the problem. Okay. So let U be harmonic and have the mean value property. Yeah, we already showed that every harmonic function has the mean value property. And then we do the following calculation. We calculate u of y times this function here. We calculate u of y times this function. Okay, then we may write this. Phi is any function with compact support in the interval. So it's a real function on the interval from 0 to r with compact support. So we may extend it outside by 0. So it's also a function with compact support on the whole real line. And okay, and then we insert here the distance, and here's also the distance. And then the claim is by polar coordinates. We may write this, yeah, since this only depends on the distance, yeah, and on the boundaries of the ball around x with radius s. This is always constant here, so we can put this out of the integral. Yeah? It's constant equal to s. Yeah, this y minus x is on this boundary of the ball constant equal to s. So we may put this out and write this as s. Okay, and then it remains this, and here we have this integral. Here this is inside. Okay, and now look at this expression here. Yeah, and you see this is the mean. This is the mean of u of x. So this is constant. Yeah, so this is constant times u of x. So this whole thing is equal to the integral from 0 to r of this real function on a real interval times u of x. So it vanishes of this integral is 0. Now this we will make now to the weak mean value property. Okay, let's see how we can do this. Also, we have a ball. Again, we have a ball. Now we don't need that the closure of the ball. We only need that the ball sits inside of omega. And we have a function psi, small psi, with compact support in this interval. And we assume that the integral is 0. So this integral is 0. So for this reason now this vanishes. And then the distribution u vanishes on the following test function. This is this function here, yeah, which is exactly this expression here. So this integral is the evaluation of the corresponding distribution on this function here. Now, why this function here is smooth and has compact support? Yeah, we claim the support sits inside this ball, yeah, because phi has compact support in the interval from 0 to r. So if the distance of y to x is at least r, yeah, then everything here is 0. Then this is 0 and this is 0. Okay, now the absolute value y minus x. This is square root of y minus x squared. So as a function, y to y minus x, this is smooth on Rn, and there's one exception, yeah, the square root. This is of course if y is equal to x. On this set, it's smooth. So as long as this distance is non-zero, this function is smooth. And since psi is smooth, everything here is smooth. Yeah, so since this support must not contain 0, yeah, this means psi at 0 vanishes. Yeah, so in the neighborhood of 0 it vanishes, and so we have no problem at this point. So it's really smooth. So this shows that this is really a smooth function. It has this support, and then now the weak mean value property is that a distribution vanishes on all these functions, yeah, with these properties, where psi has this property and this property. This is the mean value, the weak mean value property. And now we want to prove, yeah, now we want to prove first that a harmonic distribution has this weak mean value property. And later we will prove the reverse. Yeah? Weil's lemma will prove the reverse and will even prove a stronger statement than the reverse. Okay, we already understood that the harmonic distributions are those distributions which vanish on this function. So we have to show that there exists a function g whose Laplacian is f. Yeah, because on any such functions a harmonic distribution vanishes. Yeah, and this is the only way how we can show that a general harmonic distribution. So we need to show that there exists such a function with this property. Now, first observation. Since, yeah, and this is quite nice, yeah, since this has compact support and since this integral is 0, we claim there exists a function with compact support inside this interval, antiderivative of small psi. Yeah, now let's draw a picture. Yeah, we have our function psi. Yeah, here is r. So here we have our function psi. Okay, this is the function psi. And now, of course, since the support is contained here, has compact support somewhere here. Now we calculate the integral. Yeah, now we calculate the integral. This is, of course, here 0. And then the integral. Yeah, then it goes up, then here again goes down, and so on. Okay, and sorry. And after here, when we reached the boundary of the support of psi, then it's again constant. Yeah, it's constant here. Here we assume it's 0. We start the integral from here, and then it's constant. And of course, in order to make that psi, this is the function psi, if this should have compact support, then it must vanish here. So this means the integral of psi, of small psi, has to vanish. We need this condition, yeah, to find this function capital psi with compact support. Because otherwise we might have that here some non-zero constant if it's here 0. Yeah, we can only have such an antiderivative with compact support if we have this condition. Okay, but we assume this, so we find this condition. Yeah, if the integral is 0, then finally here psi will be 0. Yeah, here the constant is exactly this integral. Okay, so we have this function. Now we define our function v of t. Yeah, we define this function v of t. Yeah, and this is a function depending on one real variable. Yeah, it's a function on one real variable, and we start by r. We start here and integrate this function, which is already an antiderivative of the small psi. Okay, and then the claim is for large t, yeah, this is clearly 0, yeah, because if t is larger than r, yeah, then this is always 0. So for large t, for large positive t, this is 0. Yeah, it can only be non-zero for small values. Yeah, and but also for small t, what we can say about the function v of t? What we can say? Yeah, because we know that for small s, psi of s is 0. So we know for small t, phi of t is constant. We don't know that it's 0, but if we are smaller than the support of small psi, and then we are also smaller than the support of capital psi, and then v of t is constant. And now we define g of y just as v of this distance. Okay, this is clearly a function with compact support. Yeah, and now we already know, yeah, since this is a function which depends only on the distance to some point, and since the Laplacian is invariant with translations, we already know our formula how the Laplacian of g depends on v. Yeah? It's exactly this formula. Yeah? Remember? Yeah, we derived this formula in the fundamental solution here. We calculated this. And this is not only true for if it's the absolute if it's the distance to 0. Yeah? By translation invariant, the same holds if it's the distance to any arbitrary point, which we here choose as x. Okay, so we have that the Laplacian of g is this expression. Okay, so we insert. If we take the second derivative of t, yeah, here the only t dependence is here. First derivative is insert psi, insert this psi, and second derivative then by the fundamental theorem of calculus we get this. This is the second derivative. Now, yeah, so this is the second derivative. Then we get this term and this term, and the first derivative is psi of s, maybe I should write this, phi prime of t is equal psi of t divided by n times t n minus 1 omega n. Yeah? This is the first. And if we take the second derivative, phi double prime of t, yeah, okay, then we get one term. We should take here the derivative, which is small psi, psi of t divided by n times t n minus 1 omega n. And then we should also take the derivative here. Then we get an n minus 1. Yeah, then we get here an n minus 1 over n, this power to the n minus 1 omega n, and of course, yeah, if we if we take the derivative of n minus 1, yeah, then we get an additional factor here. Yeah, so if we do the calculation here, so maybe I write this. So what is the next term? It's minus n minus 1 times capital psi of t divided by n times t n times omega n. Okay. So for this reason we get this term with this minus, and then we get this term, yeah, which is with this term is this term. And then you see this and this term, they cancel. Yeah, this is the nice thing. These two terms, they cancel. This is how we build this function. So it remains this term. Yeah, and this term is exactly f. So we get f. So we see that this function really has the property that the Laplacian of g is f. So this proves that that any harmonic distribution has the weak mean value property. Okay, there we stop. Next time we'll show the reverse. So what we have done today, let's recall what we have done today. We introduced the mean value property. So we showed both direction. Yeah, we give a complete characterization of harmonic functions. We proved this with this very nice trick using the divergence theorem and the mean value. Then we had this nice this strong estimates for all derivatives. We had this Liouville's theorem, and we showed that any harmonic distribution solves the weak mean value property. So we generalized our mean value property to a weak mean value property, which we can also apply to distributions. Thank you.